All right, in this lesson we want to cover section 2-4 in the text. It's about time derivatives of vectors. All right, so we need to be able to do this because we're going to take time derivatives of vectors all the time. We need to differentiate position vectors to get velocity vectors and differentiate velocity vectors to get acceleration vectors. So it's something we just have to become familiar with, and it's a little tricky. And it's tricky because of this. A vector has a magnitude and a direction. If the magnitude changes, but the direction does not, obviously there's a time derivative to the vector. But similarly, if the magnitude is constant, but the vector is rotating, there is also a non-zero time derivative. So we have to be able to deal with derivatives taking into account both the change in length and the change in direction. And it's this direction part that makes it a little bit tricky. So think of a vector A, which has some direction denoted by this unit vector u hat sub A. And at time t plus delta t, it moves, right? So if this is A at time t, at t plus delta t, it might rotate to this position and then get longer. And so if you kind of put the tails together of these two vectors, A was here, it rotated through some angle delta theta and got longer. So there's a component of the time derivative due to the magnitude change and a component due to the rotation. We're going to write A as a magnitude, which is time dependent, times a unit vector, which is also time dependent, and then we're going to differentiate term by term. Okay? So we write A this way, we take the time derivative of the whole thing, and so we use the chain rule to do it piece by piece. The first term is dA dt times u hat sub A, or A dot times u hat sub A. That's the term that deals with the change in the magnitude of A. But we also have A times the time derivative of u hat sub A, time derivative of the unit vector, or A times u hat sub A dot. This is the component of the time derivative of A that deals with the rotation of A. So we need to be able to deal with both of these. This one's pretty straightforward. This one's a little more complicated and takes some further discussion. All right, so we can think about the rotation of a vector as a door swinging around a hinge. So we have in this picture a door. There's a hinge right here along this line. That's fixed. And as the door rotates, its point A stays fixed. Point B goes around in a circle. Okay. So this door swings around at some angle theta, right? We can use theta to denote the position of door as it rotates around the hinge, and we can use omega to relate to denote the velocity, the angular velocity of that door. So that omega tells you how fast this angle theta is being covered or changed. Okay, so we have a rotational position, theta, a rotational velocity, omega. We can go one step further. So omega is just the time derivative of the angle. If we take the time derivative of omega, we get an acceleration. It's an angular acceleration, and it's the time derivative of omega, or the second time derivative of theta. Okay, so omega has units of radians per second, alpha radians per second squared. Okay, we also will talk about this fixed line as the axis of rotation. Now, what we end up doing, and I'm just going to cover this briefly, is we end up writing the angular rotation vector as a vector which is perpendicular to the axis of rotation. So if we have some line here which is sweeping out some angle gamma, then the angular the rotation vector is written perpendicular to the plane of rotation, and the magnitude of that is gamma. So we have a unit vector perpendicular to the plane of rotation, u hat sub gamma, and the magnitude of this rotation vector is the magnitude of the angle times that unit vector. And we use the right-hand rule to figure out which direction we make this vector. So we wrap our fingers in the direction of positive angle change, and then our thumb points in the direction of positive rotation vector. So this is the key to the whole thing, is we have this rotation vector which is perpendicular to the plane of rotation. And so it's a little odd to have it perpendicular, but it's the way the math works out right. Now the next few slides here go through kind of a crude derivation of how you take the time derivative of a vector. You can take a look at these if you want, or look in the text. I'm just going to skip ahead to the end result. Okay. So here's the key. If I have some unit vector, u hat sub a, it does not change in magnitude, but it changes in direction. It's sweeping through some angle theta at a rate theta dot, or an angular velocity omega sub a. Okay, and as it turns out, the time derivative of that unit vector is the angular velocity vector, which is perpendicular to the axis of rotation, crossed with the unit vector itself. So you take the cross product of the angular velocity vector and the unit vector, and that gives you the time derivative of the unit vector. Now this is for a vector which is fixed in magnitude, unit magnitude. So this only handles the rotational part. To get the time derivative of an arbitrary vector, we have to add in the magnitude changing part also. Okay. The key is that this cross product gives you a vector which is perpendicular to both omega a and ua, and so it's tangential to this circle of rotation. All right. So this is the key result. U hat dot is omega u crossed with u itself. Now let's return to our time derivative of a general vector. So we have a general vector a. We're taking the time derivative, so we're taking a dot. It's the time derivative of the magnitude times the unit vector for a, plus a times the time derivative of the unit vector. And the time derivative of the unit vector we just saw is this omega cross u itself. And so the time derivative of a general vector is the time derivative of the magnitude times the unit vector for that same vector, plus the rotational vector crossed with the vector itself. This is the magnitude change term. This is the rotation term. Let's say a is a position vector, then this gives us the velocity vector. If we want the acceleration vector, we take another derivative, and then we have to go through this thing and go term by term and differentiate everything using the chain rule, so it gets a little messy. The second derivative of a vector is the second derivative of the magnitude times the unit vector for that vector itself, plus twice the rotational vector crossed with a dot u hat sub a, plus the time derivative of the angular velocity vector crossed with a itself, plus the angular velocity vector crossed with omega cross a. All right, so it's a little messy, but if you're careful about writing down all the components of a, you can fairly easily take either one or two derivatives. Okay, so let me just make a quick comment about what each of these terms is. So this first term is a term associated with the acceleration of a in the direction of a if it weren't rotating. If it's not rotating at all this goes away, and this is the linear acceleration in that direction. This term is the Coriolis acceleration. We'll come back to that as we go through the semester, so I won't say any more about that. This omega dot cross a is the component of the acceleration of a perpendicular to a, right? Remember I said it's tangential. If the magnitude of a were held fixed, right? So if a is only rotating, so this is the component of the acceleration perpendicular to a. And then this last term is the component of the acceleration of a perpendicular to omega a if the magnitude of a were held fixed. All right, so let's do a couple quick examples. So first one has to do with tracking of an airplane. So an airplane is flying horizontally left to right on the screen. There's some tracking station in the lower left corner that has to track the airplane. So it's constantly pointing at the airplane, and as the airplane flies, this tracking station is rotating with some angular velocity omega. Okay, and in order to be able to track the plane, you need to be able to relate the angle of the tracking station and its angular velocity to the geometry of the problem, the height of the plane, the speed of the plane, that sort of thing. Okay, so we just want to find a relationship between theta and theta dot for this tracking station and the velocity of the plane. So here's our picture. We have the tracking station with the origin of the coordinate system on the tracking station. The tracking station is some height HA from the ground. The plane is a height h from the ground. We draw a position vector r from the tracking station to the plane, and we have an angle theta, which gives the angle of that tracking the position vector relative to the x-axis. Okay, the plane is flying horizontally, so it has some velocity v naught, and then the direction is given by the unit vector in the x direction. Okay, so there's a u hat sub r, which is the unit vector along r, and a u hat sub theta, which is a unit vector perpendicular to that, but still in the xy plane. So we can just relate h to ha plus r sine theta, right? So r sine theta is this height here. And then to find the velocity vector of the plane, we can just take the time derivative of r. So r dot is v, and that's given by r dot, the time rate of change of the magnitude, times u hat sub r plus omega r cross r. And omega r, because these rotation vectors are perpendicular to the plane of rotation, omega r is theta dot k, right? Where k is unit vector in the z direction, which is coming out of the screen for us. Or we can write this as omega k hat. So that's one relationship for the velocity of the plane in terms of r and u hat sub r and u theta hat and r dot. But we can also write that the velocity of the plane is just v naught times I hat, and we can equate the two. So v naught I hat we can also write as v naught times cosine theta u r hat minus sine theta u theta hat. So this is just I hat broken up into radial and tangential components. And this is also given by r dot u hat sub r plus r omega u hat sub theta. This is what we got from formally taking the time derivative of r. And we can just equate the radial terms here and the tangential terms, and that gives us two equations. So v naught cosine theta is r dot, and minus v naught sine theta is r omega. So these are two relationships relating r dot, theta, and v naught, or r and omega and theta and v naught. And if we just solve these for v naught, we can eliminate v naught and write that r dot over cosine theta is minus r omega over sine theta. So these are the relationships we were looking for, and we could use those to do the tracking if we were so inclined. Right? So that basically finishes that problem, and it's just giving us an example of using these time derivatives of vectors. So let's do one more. Suppose we have a merry-go-round, which is spinning. It's in a park, it's spinning. There's a child on the merry-go-round. The child is walking on the merry-go-round. So we're told that the child is walking at 4 feet per second, perfectly radially on this merry-go-round. But the boy is also spinning. So the velocity vector of the boy has a radial component and a tangential component. And we're asked to find the velocity and acceleration of the child, or a point P on the child, when the child is half a foot and 2.3 feet from the center of axis of the rotation. Okay. So we just, if you look vertically, we have our origin of our coordinate system at the center of the merry-go-round. We have a position vector r, which represents the position of the boy. There's a unit vector in that direction. There's a unit vector perpendicular to that, but in the plane of rotation. There's also a unit vector in the z direction, come right out of the screen at us. There's an angular velocity omega of the merry-go-round. The velocity of the boy can be written as the time rate of change of the magnitude of r times the unit vector in the r direction plus omega r cross r. Okay, and that'll be in the q direction. Okay, now r dot we're given, that's 4 feet per second. We're told he's walking radially at 4 feet per second, so that's a given. R dot is 4. The angular velocity, we're told that this thing rotates once every 2 seconds, so half a turn per second, or pi radians per second. So omega is 3.142, or pi radians per second. And again, because these rotation vectors are perpendicular to the plane of rotation, then in this case, by the right-hand rule, the rotation vector is out of the screen, coming right at us. Okay, so we can just write down these terms formally. The velocity of the boy is the time derivative of the position vector, which is 4ur hat plus pi k hat crossed with r ur hat. K cross ur hat gives you uq hat. So it's 4ur plus pi r u hat uq hat, and the units are feet per second. We put in values of r, and out come the two velocities. So at half a foot, the velocity vector is given by this. At 2.3 feet, it's given by this. If you want to know the speed of the boy, you find the magnitude of this velocity vector at either position, and you'll have that. Notice that the velocity vector increases as the boy gets out further because due to the spinning, he's moving faster the further out it gets. Now let's do the acceleration. Again, we just write down this ugly expression for the second derivative of a vector. Because the boy's walking at a constant rate radially, the second derivative of r of the magnitude of r is 0, right? So this term is 0 because the boy is walking at a constant rate. Also, because the merry-go-round is spinning at a constant rate, omega dot is 0. So this first term is 0, the third term is 0, and our acceleration comes from just the second and fourth term. So we write down those second and fourth terms. Then we just start plugging them in. Omega r is just pi k hat. So we plug that in. R dot ur is 4ur hat. And then for this term, we write pi k hat crossed with pi k hat cross r ur hat. So here, k crossed with ur is just uq hat. And then we just do the math here. And so we get 25.13 uq hat. Here we leave the first omega there, and we do this cross product here. K hat crossed with u hat is minus, k hat crossed with ur hat is uq hat. And then k hat crossed with uq hat is minus ur hat. Okay, so then we do the magnitude is 9.87 times r, and then it's ur hat. So this is the acceleration vector. For different values of r, we plug it in, we get accelerations. So at half a foot, we get this. At 2.3 feet, we get this. Again, it's increasing as we go out because of the change in radius. Okay, so we can find the magnitude of these to find the acceleration of the boy. So if we want the magnitude of acceleration at 2.3 feet, you do the square root of the sum of the squares of the components, and you get 33.8 feet per second squared. That's higher than the acceleration due to gravity, so that's more than 1 g for this poor little child. That sounds high, but so is 30 RPM. So spinning this thing at 30 RPM gives a pretty good acceleration for the child. Okay, so that's a couple quick examples of how you apply these vector time derivatives.